All right, let's get right into it. We're always hearing about these gigantic, super powerful AI models. But there's a huge catch. How do you get all that power to run on something, smaller than a data center? Today, we're going to pull back the curtain on a really clever trick that makes these massive models faster, smaller, and way more efficient. It's a game changer.
So to really wrap our heads around the problem, look at this number. 30 billion. That's not a typo. That's roughly how many different math operations, we call them flops, a pretty standard model like VGG16 has to do just to figure out what's in a single picture. It's an absolutely staggering amount of work, and that, right there, is the mountain we have to climb.
Which, of course, leads us to the million-dollar question, doesn't it? This is the core dilemma we're facing. We all want that incredible intelligence, that power that comes from these huge models. But we also want it to work on our phones, in our cars, on devices that aren't plugged into a power plant. So how in the world do you shrink these things down without, making them dumber?
Okay, so before we get to the magic trick, we really need to dig into what we're up against. This is what we call the AI size problem. And trust me, it's a big one.
Yeah, the growth has just been insane. It's literally exponential. What this means is we've created a massive bottleneck. Researchers are cooking up these amazing, mind-blowing models in their labs. But getting them out into the real world, that's a whole different ballgame. Your phone, your laptop, they just don't have the muscle to run these behemoths. It's like trying to stream a 4K movie on dial-up.
Let me put this in perspective for you. VGGNet, which is kind of like a classic car in AI terms now, took up over 500 megabytes. That's just for its internal brain, the numbers it uses to make decisions. That's bigger than a lot of apps on your phone. And honestly, today's models make 500 megs look like a rounding error. So you can see why this is a huge, huge problem for getting AI onto regular devices.
So the obvious answer is, just cut stuff out, right? Make it smaller. This is called pruning, and it makes a ton of sense. But it turns out there's a really tough choice you had to make.
Okay, so there were two main ways to do this. Think of it like this. On one hand, you have unstructured pruning. This is like going through a garden with tweezers and pulling out individual weeds. It's super precise, you can keep the model really accurate, but you end up with a random, messy pattern. Then you have structured pruning. This is more like taking a lawnmower to whole sections of the garden. It's clean, it's fast, and computer chips love the organized pattern. But you can easily end up chopping down a lot of flowers you wanted to keep, hurting the model's brainpower.
And this right here nails the problem with that precise, unstructured method. Basically, even if you make the model smaller, the computer chip gets lost. It's like trying to find a specific book in a library where all the books have been thrown on the floor. The information is still there, but it takes forever to find anything. So you get a smaller model that isn't actually any faster to use. Kind of defeats the purpose, right?
So that was the standoff. That was the big, frustrating trade-off for years. You could have an accurate model that was still slow, or you could have a fast model that was a little bit dumber. Pick your poison. It was a classic case of not being able to have your cake and eat it too. But what if you didn't have to choose? What if there was a way to get the best of both worlds? Well, that's where NVIDIA came in, with a truly elegant solution. It's something that feels a little bit like a magic trick. This is the big idea. It's called 2-4 fine-grained structured sparsity. I know, that's a mouthful, but the concept is actually beautiful in its simplicity. It's kind of in between the two methods we just talked about. The rule is just this. You look at any tiny group of 4 connections, or weights, in the model, and you make sure exactly 2 of them are 0. That's it. It's a simple repeating rule that instantly cuts the model size in half.
And this is the genius of it. That simple 2 out of 4 rule creates a predictable pattern. It's not totally random, so specialized computer chips, like NVIDIA's sparse tensor cores, can be built to recognize it. The hardware knows the dance steps, so to speak. It knows it can just skip over every other pair of values, which makes it super fast. You get that fine-grained precision, but with a structure the hardware can actually use. Now at this point, you're probably thinking, okay, that sounds cool, but it must be a nightmare to actually implement. But that's the other brilliant part of this. It's not. There's a super simple 3-step recipe for it. Okay, here's how you do it. First, you just take your regular, fully trained smart AI model. Nothing special. Second, you go through it and apply that 2-4 rule. For every little group of 4 numbers, you find the 2 smallest ones and just delete them. Turn them to 0. Now, of course, when you just chop out half the brain, the model's performance is going to dip. Which brings us to step 3. You just train it a little bit more. This lets the remaining connections learn to work together and pick up the slack, bringing the model's accuracy right back up.
So after that simple three-step process, what's the result? Well, this is where it gets really, really cool. You get something that's faster, more efficient, and, well, let's just look at the numbers.
Check this out. When they applied this to a big model, its energy efficiency, basically the bang for your buck you get out of the electricity you feed it, jumped by up to 36%. That is a massive gain. It means you can do way more work with the same amount of power, which is a huge win for everything from data center costs to battery life.
Okay, but here's the kicker. What's the price you pay in accuracy for that huge efficiency boost? What's the trade-off? Zero. Absolutely none. Because of that retraining step, the model gets right back to the exact same level of accuracy it had before. You lose nothing. It's basically free performance. It's incredible. Now, this 2-4 trick is amazing, right? But of course, the story doesn't stop there. Researchers are always asking, what's next? Because as great as a 50% cut is, maybe, just maybe, it's not the perfect solution for every single part of the model.
And that really gets to the heart of the next challenge. Is a fixed 50% haircut, applied everywhere, always the best idea? Think about it. Some parts of the AI's brain are probably way more important than others. Applying the same rule everywhere is a bit of a one-size-fits-all approach. What if we could be a little smarter about it?
And that's where things like hybrid sparsity come in. A great example is a framework called Patch. The idea here is to chop the model up into tiny little tiles, like a mosaic, and then it intelligently decides for each tile, should we leave this part alone because it's super important, or can we apply the 2-to-4 sparsity rule here? This way, you get a custom-tailored sparsity level for the whole model.
And the payoff is pretty sweet. You get even bigger speedups in the real world. By protecting those most critical parts of the network, you close the accuracy gap even more, getting even closer to perfection. The model essentially learns where it can afford to lose connections and where it can't. It's the ultimate compromise. You get that smart, flexible pruning, but in a way that the hardware can still understand and accelerate.
So you can see the whole journey here, right? We went from this impossible choice between fast and smart to this really elegant 2-4 solution that gave us both. And now we're moving towards even smarter hybrid methods that tailor the solution. It's all about finding these brilliant compromises, which makes you wonder, as these models get even crazier and more powerful, what's the next breakthrough going to be? What's the next magic trick that'll help us have it all?